Welcome back, Shaler area. This is Science Physics Note Video number 10. We're also starting part 3 of physics. So the rest of these note video series will lead up to the part 3 quiz in physics and then the physics exam, and then we'll be at the end of the year and you'll have your final exam. So what is part 3 all about? Well, part 3 of unit 3 is all about simple machines, work, and power. This is chapter 12 in the book, so you want to make sure that you go in and read chapter 12. And every section of notes that we talk about all has essential questions and ideas, and this is what all of the material boils down to. So it's a really good starting point for studying if you go back and you look at those essential questions and ideas for every section so that you know if you're getting the big ideas. So for example, in this section of notes, everything we're going to learn has to do with what work means, and work means movement. Without movement, you've done no work. There's an equation for work, so in physics we have all kinds of equations that you need to know how to manipulate and use. Simple and compound machines, what's the difference and what are they? We're going to spend a lot of time talking about mechanical advantage and what that is. We're going to be calculating efficiency of machines, and what is power, and how do I figure it out? So the rest of these note videos that you're going to be watching all have to do with these essential questions. Well, time to get to work. Work is what happens when you exert a force on an object, and then because of that force, you make it move. So a couple of caveats to make sure that you know. If something doesn't move, no work was done. You could spend all of your energy and all of your time pushing on a wall and ramming yourself into a wall and just exhaust yourself completely pushing on a wall. But if you don't ever make that wall move, you have done zero work today. All right, from the physics definition of work, you have to make something move in order for work to be accomplished. The other caveat is that the direction that you're applying the force has to be in the same direction of movement. You can't push an object from the side and then have it go forward and say that that's because of your force. Now, once you get into higher levels of physics, you will be doing lots of things with angles, and you can figure out how much of the force at an angle turns into how much work at a different angle, but that's something that you will figure out once you learn some geometry. So every kind of measurement that we discuss has a different kind of unit associated with it, and the SI unit of work is called the joule, named after Mr. Joule. 1 joule is the amount of work that needs to be done to move a 1 Newton object the distance of 1 meter. Now the equation for work is pretty simple. It's just force times distance. So if that means, if that means 1 joule is equal to using 1 Newton over a distance of 1 meter. So a joule is essentially also called a Newton meter. So that's the same thing. A joule and a Newton meter are the same thing. Well, let's break that down even more. Here, let's see if I can get a whiteboard up here. I didn't know those things would stay. That's interesting. Eraser. So what's a Newton? This is where all these units start to come together. So remember, a Newton is equal to a kilogram meter per second squared. So if we have a Newton meter, that means we can multiply all of this by meter. So that means a Newton is also equal to a kilogram meter squared per second squared. So we could go all the way back. I could give you information about how long it takes an object to move a certain distance and its mass, and you can multiply all of these things together. So if you know an object's mass and you know its acceleration, it's meters per second squared, and you know the distance that it accelerated, another meter, you can combine all those things together to make the kilogram meter squared second squared, and you could solve for work. Because then in that case, this would become a joule. So all of these things layer and build. So, practice problem 1 for work. In an earlier problem, we figured out how much force was needed to bench press. We calculated that in order to bench press 100 pounds, you had to use 450 newtons of force. Well, let's figure out how much work gets done if the person who's doing the exercise has an arm that's 0.8 meters long. Well, work is force times distance. So 450 newtons times 0.8 meters would mean that this person has done 360 joules worth of work. Well, in this problem from before, remember we calculated how much force the engine of my car uses when my car accelerates to 60 miles an hour in 4.5 seconds. And we calculated that by, we did a lot of conversions here. I don't know if you remember this problem or not, but we had to convert the pounds to kilograms to get the mass. Then we had to figure out the acceleration from 0 to 60 in 4.5 seconds, and then convert that to meters per second squared. And in the end, though, we figured out that my car uses a force of 7,800 newtons to accelerate from 0 to 60. Well, if I use 7,800 newtons to accelerate to 60 miles an hour, but I do that over a distance of 60 meters, we can figure out how much work the engine of my car is doing. So it is force times distance. So if I accelerate from 0 to 60 using 7,800 newtons of force, and I do that over a distance of 60 meters, that means my car is doing 468,000 joules of work. Well, once you start to get numbers that are this big, we can start to use the SI prefixes as well. How many kilojoules would that be? Well, kilo means 1,000, so that means 468,000 joules would be equal to 468 kilojoules. Remember, those prefixes aren't just, like kilometer or kilometer or kilogram. You can apply those prefixes to any of the units. Power is the last type of measurement that we're going to discuss. And power has to do with the rate at which you do work. So it takes the same amount of work, you accomplish the same amount of work if you carry a load of shingles up a ladder, if you do it in 30 seconds, or if you do it in 30 minutes. The same amount of work has gotten done. You have moved the same mass, the same distance. So to pick up that mass, you had to use force. But if you move that force over the same distance, which would be the height of the ladder, it doesn't matter how fast you do that. Work has no extra factor of time involved in it. When you want to know how fast you are doing work, now you're talking about power. Power is the rate that work is done. So the faster that you accomplish work, the more powerful you are. Power is work divided by time. And the SI unit for power is called the watt, which you are most familiar with things like light bulbs. Now, when you think of light bulbs, you think of the watts as the brightness of the bulb. And you typically don't think about light bulbs as doing work, right? Because they're not moving. Well, it's not necessarily that the light bulb is doing work, but it's the amount of power that gets used to make that light bulb glow. And that power can be applied to other things. So when we measure power of lights, it is the same measurement. It is how much work that could be used to move a certain object a certain distance, but now we are applying it to the actual amount of energy that we are using to make the light bulb glow. So power is work divided by time. So that means it is a joule divided by a time, in which case a watt is 1 joule divided by 1 second. So if we pull out our whiteboard here again, a watt, 1 watt, is equal to 1 joule divided by 1 second. Well, that also means that 1 watt is equal to 1 Newton meter divided by 1 second. That would also then, remember, mean that 1 watt would be equal to 1 kilogram meter squared over second squared second, because we added another second to the bottom, and that means that these seconds would come together, and if we break down a watt to its base parts, can't write today, a watt would be a kilogram meter squared second cubed. So all of these units just build on top of one another, and we just add another unit to the mix and we get a new measurement. So the only difference between work and power is an extra second down here on the bottom. We've gone from second squared to second cubed. All right, so now instead of 1 bench presser, we have 2. We have 2 bench pressers working out side by side. They're doing the same. They're bench pressing 100 pounds like they were before. So we figured out that before it took like 450 newtons to bench press, 450 newtons of force to be able to bench press 100 pounds. And we discussed how the arm is 0.8 meters long on these people. So that means that they're doing the same amount of work. They're doing 360 joules worth of work, but if one of them does a rep in 1 second and the other one does a rep in 2 seconds, well, which person's more powerful? Well, if power is work divided by time, 360 joules is the same amount of work for both of them, but one of them is doing it in 1 second, the other one is doing it in 2 seconds. So that means person number 1 is using 360 watts of power, while person number 2 is employing 180 watts of power. So person number 1 would be twice as powerful as person number 2, even though they're accomplishing the same amount of work. All right, so how powerful is my car? Well, if you remember, we talked about how my car accelerates from 0 to 60 miles an hour in 4.5 seconds, and it has this mass, and we used all of that information to find out how much force in newtons the engine was being able to use. And then in the last problem, we figured out how much work was done if that is accomplished in 60 meters. Well, now let's see how powerful the motor is. Well, the work we figured out was 7,800 newtons in the 60 meters, which gives us the 468,000 joules. Well, power is joules divided by time. What was the time? How long does it take the car to accelerate from 0 to 60? It was 4.5 seconds. So if we have the work in the certain amount of time, we can figure out that my engine is 104,000 watts. So I have a 104,000 watt engine, or 104 kilowatt engine. What's that mean? How can we call an engine in watts? We're not used to that in the United States, because what measurement, what unit do we use in the US to talk about the power of a car engine? We use horsepower. Well, it just so happens that 1 horse can exhibit 746 watts of power. So that means in this 0 to 60 acceleration, what would be the horsepower of the car? Well, 104,000 watts. If 1 horsepower is 746 watts, that means the motor is 139 horsepower. But wait, if you do a quick Google search and you look at my car, 2003 Dodge Neon SRT4, it tells us that the motor of my car is 215 horsepower. Why is it that when we did the math, we got 139 horsepower instead of 215 horsepower? Does that mean that the physics is wrong? No, that's kind of the difference between working out problems in class and doing things in the real world. Remember, there's a certain amount of friction that gets involved, the friction between the tires and the road, we have stuff going on inside the car, but most of the difference is thinking about what we're actually solving for and what this means. So when they tell you about a car's horsepower, they are telling you about the amount of power that the car has at one certain spot in what the car is doing. So sometimes you will see this and sometimes you won't, but my car has 215 horsepower at 5,200 RPMs. If you have a car that is a stick, sometimes automatics have this too, on the gauge you have two dials. You have the speedometer, which tells you how fast you're going, and you have the tachometer, which tells you how fast the engine is moving. So not how fast the wheels are turning, which is your speedometer, but how fast the engine is rotating, we'll say, because RPM stands for rotations per minute. Because the way the engine works, we learned about this when we learned about thermodynamics and heat and how the extra heat causes the gas to expand, which moves the piston. There was a picture in a previous note, and it shows how the pistons go up and down, and that turns the crankshaft, and that crankshaft ends up turning the tires. Well, it's the rotation of all of that stuff going on that is this measurement. So if I rev up my car redlines at 6,000 RPMs, I think. So if I get my car to 5,200 RPMs, my car would then have enough power to be 215 horsepower. But what was happening in real life down here? Well, in real life down here, remember, I am not holding my engine at a constant 5,200 RPMs. This is a little bit like how when we measured speed based on the marble going down the ramp. Or if I told you it took me an hour to drive to my parents' house, which was 60 miles away. Well, I'm not going a constant 60 miles an hour. I could be speeding up or slowing down, passing cars, stopping at a red light. We're figuring out an average speed when we do that. This is sort of like that. This is like an average amount of horsepower that my car would employ going from 0 to 60. So that's why the numbers don't jive. So you have to kind of keep in mind what you're actually measuring. If we wanted to get this 215 horsepower rating, we would have to put the car on something called a dynamo, where the car stands still and the wheels are on these two big drums that when you hit the gas on the car, it makes the wheel turn, which turns these two big drums. So the car's not actually moving, but it's going really fast. Did that once on ice one time. I had the speedometer that was going really way too fast, but the tires were just spinning on the ice, and you could see how that would work out with the motor. So anyway, it doesn't seem like it's a lot of horsepower, but that's because it's the average horsepower and not the max horsepower. But you could still do this for any of your cars. You could figure out the horsepower based on the watts, based on the acceleration to 60 miles an hour, if you knew how far the car would travel to get to 60 miles an hour. And all of that is better than a 1 horsepower car. A 1 horsepower car would not be very fast. Efficiency is the last thing that we need to discuss before we start actually talking about machines. So efficiency is represented as a fraction. We have output work, and that's how much work the machine puts out. So you put a certain amount of work into the machine, then the machine does a certain amount of work. Well, the amount of work that you put in goes on the bottom of the fraction. The amount of work you get out goes on the top of the fraction, which would mean an ideal machine. So if a machine was perfect, you would have 100% efficiency because you would get just as much work out as you put in. So if I had 5 units of work I'm putting out and I'm putting 5 units of work in, then I would have, this would work out to be 1, and in a fraction 1 is 100%. So that means that I would have a perfect machine. But that can't happen. You will never get as much work out of a machine as you put in. There is always a certain amount of loss. And that is due to friction. All right? The more moving parts you have on a machine, the more that the parts rub together, you're going to lose energy to friction, which means you're going to lose work to friction. If something gets warm when you're using it, well, that's another way that energy gets lost. So in any given machine, you lose energy because of the way the machine works. And it is one of the big challenges to engineers, trying to design machines that have the highest level of efficiency possible so that you conserve energy. But you'll never get 100%. We will never build a frictionless machine. So let's do some easy examples here. Let's say your arm exerts 20 joules of work while you use a hammer. You might not think of a hammer as a machine, but that's why we're starting off easy. But the nail, so the hammer has 20 joules of work that's being done to it. When it hits the nail, only 18 joules of that work gets transmitted to the nail. What's the efficiency? Well, if we get 18 joules out, but we put 20 joules in, 18 divided by 20 would say that our hammer is a 90% efficient machine. Well, where are we losing energy from? Where would the friction be involved here? Well, there's lots of things. You're going to get friction again from the two surfaces, from when the hammer actually hits the nail. There's going to be a certain amount of friction that exists there. You're going to have friction with the air resistance when you're swinging the hammer. And if you pound on something a lot, it gets hot. Like, that's energy that gets lost. That's due to, like, internal friction. When you hit the metal of the nail, you're going to kind of compress and squeeze together all those little iron atoms, and they're going to slide around on each other a little bit. They're going to compress a little bit, and that's internal friction, and that could turn into heat. So all of these things are going to cause energy to be lost and then reduce the efficiency of our machine. How about a little bit more of a moderate example? You're going to see how all of this physics starts to work together. Now we have a machine, just some random machine, that can move a 600 Newton object a distance of 6 meters, and we know that the machine can generate 450 joules of work. What's the efficiency of the machine? So the I'm sorry, I said 450, I meant 4,500. 4,500 joules is how much work the machine can do. That's our input. We know that we have 4,500 joules of work that the machine is going into the machine. Well, how much work is going out of the machine? Well, we have to calculate that. Work, remember, is force times distance. So our formula, force times distance, our force is 600 newtons, our distance is 6 meters, so the amount of work that we're getting out of the machine is 3,600 joules. We throw these numbers up here into our fraction. 3,600 joules out, 4,500 joules in. Our imaginary machine would be 80% efficient. All right, how about a complex example? Let's go back and we'll finish up talking about my car. How efficient is the motor of my car? These numbers are all legit, by the way. So my car does use 0.02 of a gallon of gas if I accelerate from 0 to 60. And 1 gallon of gas does contain 120 million joules of energy. So let's figure out how efficient my car engine is. If I used 0.02 of a gallon of gas to create that amount of energy that was needed to accelerate from 0 to 60, remember, I did that over a distance of 60 meters, and it took 4.5 seconds. We can figure out the car's efficiency. Well, my work in is how much energy, how much work could be done in a gallon of gas. How much of this is put into my car? Well, every gallon of gas has this much possible work, or this much possible amount of energy. But what I'm getting out is 460,000 joules in 0.02 gallons. So the work in goes on the bottom of the fraction. Why is my arrow going funny things? Our work in is going to the bottom of the fraction. My work out going to the top of the fraction. Getting weird symbols here. What's going on? Oh, I can actually rotate stuff around. That's cool. I think I could actually make it. Can I make it bigger too? Oh. All right, so let's stick these things up here. 120 million joules in a gallon. That goes on the bottom. That's the work in. The work out. 460,000 joules divided by 0.02 gives us this value. Do the math on that. My car motor only works out to be 19% efficient. That seems pretty bad. It seems pretty low. But remember, there's a lot of moving parts in a car. Think about if you drive around on a car and you pop the hood. Can you put your hand on the motor? No, you burn yourself horribly, horribly bad. Car motors get super hot. It's one of the things that you have to keep an eye on with your car, because if something starts to go wrong, your car overheats. It can actually get so hot that it'll melt the metal in the engine, and literally all the moving parts will melt together and just become one big solid block of metal, and that's when your engine is blown. That's when a destroyed motor, it's just totally melted down. So 60% of all of this is actually lost in the motor itself. And then you have all kinds of other moving parts in the car. You have the drive shaft that's spinning, you have all this other stuff that's using up energy, like if I'm running the air conditioning of my car, that uses up a lot of energy. That makes your fuel efficiency drop dramatically when you're using that. But also if you open up the windows, now you're increasing air resistance because it's not as smooth, so that's also dropping fuel efficiency. Sometimes it's a just can't win situation when you're trying to maximize fuel efficiency. But there's a lot of things that go on with this. So really, the maximum that my efficiency could be would be 40% if we're losing 60% to the motor itself. And that's one of the big challenges with auto engineers, trying to design ways to increase this efficiency, because that was one of the big, most recent pushes with like environmental stuff. We want to try to get as far as we can on as little gas as possible. So how do we increase the efficiency of our cars? Well, one of the things that they did was they lowered the horsepower. So, you get these tiny little cars that get lots of miles to the gallon, but they don't go very fast. They don't accelerate very quickly. We try to make the cars a little bit lighter, because the heavier the car is, the more energy it's going to take to move it. But then you kind of give up safety. It's part of this cost-benefit analysis that goes on. Well, one of the things that will ultimately probably have to happen is we'll probably ultimately have to change the way the motors work themselves. The motor design, the internal combustion motor, hasn't changed for a really long time. There are a couple of interesting designs that have come out along the way. There's a Wankel motor, also called a rotary motor. But mostly all of the engines work the same way. We're just trying to figure out the best way to make that work. But maybe one of you will grow up and design a whole new different way for an internal combustion motor to work, and you could double, triple, quadruple the efficiency. You'd be a billionaire. So anyway, this was work. This was power. And after today, we can start to talk about machines. So you have 11 questions. Be ready to solve for things like work and power and efficiency. Good luck. Don't forget to do the exit slip. I'll give you some practice questions.